In this problem, suppose a lamina corresponds to the region between the curve y equals cosine x and the x-axis from x equals 0 to x equals pi halves, given that the lamina has constant density rho of xy equals just rho. Calculate the moments of inertia I sub x, I sub y, and the radii of gyration x double bar and y double bar. Okay, just a reminder here what x bar bar is. It's the square root of 1 over the mass times the double integral over the region which corresponds with the lamina of, well, we have to throw in an x squared here, and then the density function, rho of xy dA. And this guy right here is I sub y. Because remember, x is measuring a distance from the y-axis. And then similarly, y bar bar is the square root 1 divided by the mass, remember m stands for the mass, double integral over r, y squared, rho of xy, whoops, and then we need that dA on the end. And then this guy in here is I sub x. Draw our picture, as we always do. And if this hash mark here represents x equals pi halves, so this is the x-axis, this is the y-axis, and this is 1, then between 0 and pi halves, the cosine function looks like that. So the first thing we're going to want is mass. So the mass, what's the mass going to be? Well, the mass is going to be obtained by evaluating the integral of the density function, right? But in this case, the density is constant. We can bring it out front. If you use the standard vertical rectangle to help you set up the integral, we'll use that corresponds with the dy dx order of differentials. And of course there's a 1 in here. The limits of integration go from 0 to, this function is the cosine function. And then that's from x equals 0 to pi halves. So y goes from 0 to cosine x, x goes from 0 to pi halves. Anyway, this isn't too hard to integrate. If we do that, well, let's evaluate the inner integral first. We get rho times the integral from 0 to pi halves. Okay, we integrate this, we get, with respect to y, 1 with respect to y, we get y evaluated from 0 to cosine of x dx. And then that of course, just if you apply the fundamental theorem, that gives you a value of just cosine of x for your integrand. Okay, let me free up some space here. Okay, so what does that equal? Well, integral of cosine of x is sine of x. We still have this rho on the outside. Sine of x evaluated from 0 to pi halves, which is just going to be sine of pi halves minus sine of 0, or just 1 minus 0, times rho. So the mass is actually going to be rho. Okay. So now let's go ahead and find I sub x. So I sub x, remember, we're going to use this part of y double bar. I sub x is going to be equal to the double integral. Okay, use the mass integral as kind of a template to help you set this up. Take a look at that guy. Okay, we're not going to take the 1 over m, we just need the double integral itself. So how about 0 to pi halves? Limits of integration don't change. 0 to cosine x. And then we're going to plug in y squared. And then the row can be brought out. The row of xy is a constant, so we can bring that out. And then dy dx. So we need to try to evaluate that integral. Let's see what happens. When we integrate y squared with respect to y, we get 1/3 y cubed. Okay, I'm going to bring the denominator of 3 out front. Get rho over 3 times integral 0 to pi halves of, okay, we've got y cubed then evaluated from 0 to cosine of x and the dx. And so we get something that looks more complicated than it really is to integrate. We get the integral 0 to pi halves of cosine cubed x dx. But there's a technique for integrating this thing. We're going to save a factor of cosine. This is a technique you learn in calculus too. Save a factor. If you have an odd power of cosine or sine, save a factor of the base. In this case, the base is cosine of x. So I'm going to save a factor of cosine of x to be part of my du. I'm going to use u substitution here. And then replace cosine squared with 1 minus sine squared. And then du, well, u, just let me write it off to the side, u is equal to sine x. And then you have your perfect du. Du is equal to cosine x dx. And then this guy is really 1 minus u squared. But I'm not actually going to make the substitution, but I'm going to pretend like I did. So if I actually made the substitution, I integrated, I'd get u here. When I integrate 1 with respect to u, I'd get u, but u is really equal to sine of x, so I do that integration, I get sine of x right there. And then, well, minus u cubed over 3, that's minus sine cubed x over 3. Evaluated from 0 to pi halves. And that turns out to be rho over 3. Okay, that's 1 sine of pi halves. Plug in the upper limit, fundamental theorem. Sine of pi halves is 1. Plug it in here, sine pi halves cubed, still 1 over 3. Then you plug in 0 for both the sine function here, and you get 0. So that ends up being a rho over 3 times 2/3, which is 2 rho over 9. So that's I sub y, I sub x, excuse me, that's I sub x. I sub x is 2 rho divided by 9. Okay. Now let me erase this. And in kind of parallel here with what I just did, I'm going to set up I sub y for you. I sub y then is going to be, okay, I sub y is going to be the double integral over r of x squared, rho of xy, which is just rho, dy dx. Same limits of integration as on the first two integrals. 0 to pi halves, 0 to cosine x. And we need to try to integrate this. And well, I'll do part of it for you, then I'll have you guys finish it. Okay, we can bring the rho to the outside because it's a constant in this case. Not in every case, but in this case. And then If you integrate with respect to y, you can keep the x squared on the outside of the evaluation brackets, and you just get y evaluated from 0 to cosine x dx. And then after you apply the fundamental theorem, you'll see very quickly that you get rho times the integral 0 to pi halves x squared cosine x dx. And I'm going to let you finish this integral off, but I will tell you how to do it, and it's something you're going to have to look up. So you see x squared times cosine of x. You see a polynomial, a monomial in this case, times a trig function, or more generally a transcendental function. And you want to integrate it. And that's a big clue to use a technique from Calculus 2 called integration by parts. And in fact, you're going to want to use integration by parts twice on this. Isn't that awesome? You get to double your fun here. So well, I'll just say it this way. I'll say use integration by parts twice. Integration by parts, IBP, twice. And you should get, if you do that, rho times pi squared divided by 4 minus 2. But I want you to try that on your own. If you don't remember integration by parts, I want you to look it up. Okay, and then, so we have I sub y. That's the moment of inertia with respect to the y-axis. And then we have I sub x, the moment of inertia with respect to the x-axis. So x double bar is going to be basically the square root of 1 over m times I sub y, which is, okay, the same as the square root of 1 over rho times this guy, rho times pi squared over 4 minus 2. And so that simplifies to just be the square root of pi squared over 4 minus 2. Y double bar is going to be equal to 1 over m times I sub x. Well, that's just 1 over rho, square root of that. 1 over rho times, well, I sub x was 2 rho divided by 9. So 2 rho divided by 9. And of course you get square root of 2/9, which is equal to the square root of 2 over just 3. So there you go. That's y double bar. And then one other thing I should mention, okay, x bar bar is the radius of gyration about the y-axis. Because x, or if you think of a horizontal distance as being represented by x, that measures the distance to the y-axis. And then y bar bar is the radius of gyration about the x-axis.